This is Knowledge Engineering with Semantic Web Technologies. Congratulations, you managed to finish lecture number 3, Ontologies and Logic. So this here is the extra part of the lecture for all of you who are interested to know more about ontologies and logic. So this is not part of the official course. It means you will not get scored for this. But of course, if you're interested, you are welcome to listen. So today, we want to talk about canonical forms and why these canonical forms somehow are really important, especially for first-order logic and if you want to apply automatic reasoning algorithms on that. So let's start. You know, in propositional logic, as in first-order logic, there are lots of logical equivalences. So there is a law for commutativity, so there are laws how I can make equivalent expressions for implications, for equivalences. Then there are the De Morgan laws, then the law for double negation and stuff like that, how to treat truth values within a formula, the distributive laws. And of course, all these laws exist not only for the logical connectors and or implication and equivalence, they also exist, of course, for the treatment of quantifiers. And we have learned about how to treat negated quantifiers and about commutativity of quantifiers. And this, of course, is really difficult, and it's also, you have to take care not to make mistakes when you apply these equivalences. So the point is, especially if you look at quantifiers, you have to take care. So if the quantifiers are of the same sort, then of course they are commutative. So no matter in which order you apply them, the result, of course, in the end will be the same if you consider only universal quantification or existential quantification. But if you mix both, so if you have an existential quantification over a universal quantification and vice versa, you are not allowed to commute then, so to change the order of both, because this would change also the logical sense, the meaning of the expression. I can show you why. So let's look at the following example. So what do we have here? So there exists an x, and for all y, it holds that, yeah, there exists somebody who loves everybody. So there exists somebody who loves everybody. That's nice. So now let's try to switch both expressions. So what we have here, now we have for all y, there exists somebody, and this means everybody is loved by somebody. So this, of course, is, from a logical sense, completely different than the first expression. So you have to keep this in mind. Commutativity over quantifiers only if they are of the same sort. You are not allowed to change them if they are of different sort. This is extremely important when we come then to a special form of canonical form. So in the course of achieving a canonical form for a logical expression, you will have several steps, and one of them also includes the treatment of quantifiers. And there it's really important where the position of the quantifier is and which of the variables and which of the parts of the term are involved in that quantifier or affected by that quantifier. But we will see that later on. So just keep in mind commutativity of quantifiers, you have to take care. So the point is, you know, for all these logical equivalences that exist, it means for every formula, there exist infinitely many logical equivalent formulas. So this is, of course, extremely difficult if you want to compare the equivalence of two formulas, because potentially there is an infinite variety among logical equivalent formulas. So therefore, the point is, what you do is you try to find equivalence classes, and you apply or you designate to all these equivalent classes which contain formulas of equivalent logical value. You designate a most simple and unique representative of that form, simply to make clear if I can achieve or if there is an algorithm that leads straight forward exactly to that most simple and unique representative, which is called a canonical form, then you are able to compare two logical expressions, whether they compute the same or whether they are different. So these representatives are called canonical forms or normal forms. And for example, what you do definitely you apply here, for example, the law of double negation, and you get rid of all the double negation which inverts itself back and forth again. So you can write here not f instead of not f. Pretty clear, doesn't it? So what's the canonical form that we are using or applying for first-order logic if it comes to automated reasoning, where it's really important to distinguish between equivalent and non-equivalent terms? So the goal here is to transform the formulas in so-called clausal forms. What's a clausal form? So a clausal form, it's the same like a conjunctive normal form. And a conjunctive normal form is here nothing else than a conjunction of disjunctions. So you see this here, a conjunction of disjunctions here in the braces. And this also can be written in clausal form then, as you see here, simply with curly braces, where the inner curly braces are the so-called clauses, which are combined by so-called disjunctions. And in the outer braces, there is a conjunction of all what is inside. So a clause is a finite disjunction of literals. So this is what is in the inner braces. You see here disjunctive connections of simple literals. Literals means this can be negated or not negated. So not negated atom or a not negated atom. So a simple clause can be written in these curly braces, as you see here. Then a conjunctive normal form is a conjunction of these clauses. And a clausal normal form corresponds to a conjunctive normal form. So clausal normal form, usually then you are writing this in braces. Conjunctive normal form, you are writing this with the other braces and really with the logical connectors you see here. So this here then would be a clausal normal form in general. And the point is, we want to derive an algorithm how to achieve a clausal form from an arbitrary logical expression. So we want to transform formulas into clausal form. Okay, so the following steps are required to do that, and we will look into that then in further detail. First, you have to transform this, or your arbitrary logical expression, into a negation normal form. We already have heard about the negation normal form in the last part of the official lecture, lecture 3. There we have talked about negation normal form, which is mandatory to apply the tableau algorithm to description logic expressions. And the purpose of that is here exactly the same. We want to move all negation inwards, that they stand in front of atomic expressions. So that's number one, the negation normal form. But of course, this is not the clausal form. From the negation normal form, we try to get to a so-called Prenex normal form, where we move all quantifiers within the formula to the front. And then, of course, we want to avoid confusion. Therefore, we will rename variables. You will see how this will work. And then there comes a trick, because we want to get rid of the existential quantifications. And for this, we are using the so-called Skolem normal form. So in the Skolem normal form, we remove the existential quantifiers. And this, of course, can be done in a specific way. You know, there exists something, usually means, of course, I can somehow think of an individual for which a certain condition holds. And as I told you, that the position of the existential quantifier here is really important. It depends really whether there is a universal quantification in front of it or after it. And this we have to consider for the Skolem normal form. You will see that. And in the end, from the Skolem normal form, we will get to the conjunctive normal form or clausal form. And then we are done with a representation as conjunction of disjunctions. So let's start with the negation normal form. So what you do here, you use a specific bunch of available logical equivalences that you see here, and they are well suited to move the negation towards an atomic expression. So first of all, you have to get rid of all the implications and equivalences. We have already seen that for description logic. So these are the first two equivalences that you use here to transform an equivalence or an implication into a logical expression which only then contains conjunctions or disjunctions. So, and the lower one are then the negations of quantifiers. There you have to regard that when you put a negation in front of a quantifier into the bounded expression, which is bounded by the quantifier, then the quantifier changes its polarity. And of course, you also have De Morgan's laws and the law of the double negation. So what you do with that, multiple negations are removed and all negations are placed directly somehow in front of atoms. And then you have achieved a negation normal form. So we can apply this to our already known penguin example. So here you see the penguin example. You remember, yeah, all penguins are black and white, and some old TV shows are also black and white. Therefore, there exists a penguin who is an old TV show. So we already know that this is not always true. But nevertheless, we want to prove this also with an automated method. But to do this, or before we do this, we first have to get this expression into a canonical form. And we start transforming this into negation normal form. So the first thing that you see here, we want to get rid of the implications. You have here in the first line an implication which is transformed into that disjunction where the first part of the implication is negated. And we have also in the last line, you see this is the overall expression is also an implication, and therefore also the first part in front of the first brace is negated and the implication is substituted by a disjunction. So this is the very first part. But it's not still a negation normal form. We have to get somehow the negation inside, in front of the atoms. And we can do this by further transforming this. So first of all, we are using or we are trying to get inside or the first negation inside the first braces. And we see inside the first brace there is a conjunction. If we get it in there and put the negation in front of the single parts of the conjunction, this then changes its polarity simply because you apply the laws of De Morgan. But then the negation would stand in front of the universal quantifier, and you can put it further inward, so the universal quantifier changes its polarity to an existential quantification, and in the end, therefore, also then you apply here inside the braces again the law of De Morgan, and you end up then with a penguin which is not negated and a conjunction with not black and white. And you do it likewise for the overall expression to remove all of available or existing negations in there, and you end up in something like that. And this is, of course, a negation normal form because simply you see here the negations stand in front of atomic expressions. So we have achieved our goal. This is the negation normal form. But of course, this is not a clausal form where we want to get to. So the next part would be then the Prenex normal form, and this is pretty simple. So we clean up the formulas, which means the quantifiers have to be bound to different variables and then put in front to it. So the first thing what we do is every quantifier receives its own variable. Very simple. So we stay in the first row of the expression in the first line with the x. Then the second quantifier, which is a universal quantification, we substitute the x with a y. And in the third line, we substitute the x with a z. So these are then new variables over which we quantify. And then, of course, we can put all the quantifiers, but of course in the same direction or in the same order, in front of our formula. And of course, we can then say from the individual correlation between the variables which quantifier belongs to which part of the formula. So which quantifier binds which part of the formula. This is all. So this already is the Prenex normal form. So now we have to take care of the quantifiers. And this has been achieved in the third normal form, the so-called Skolem normal form, named after Thoralf Skolem, famous logician. And what you do here is the following. You remove the existential quantifiers and you start from the left and go to the right. And now you have to consider, this is here the second point, where is the universal quantifier? So if there is no universal quantifier left of the existential quantifier to be removed, then the according variable simply is substituted by a new constant symbol, because the existential quantification says there exists an individual for which something holds. And of course, we have no other constraint, therefore we substitute it with a constant. But if there is one or more universal quantifications left of the existential quantifier that should be removed, then the according variable is substituted not with a new constant, but with a function sum symbol with arity n, which exactly corresponds to the n universal quantifiers we have left of that, and over the arguments of these universal quantifiers, simply because the individual we are talking about is dependent on the assumptions and the statements that are bound by the variables that are before the existential quantification. There is a dependency. We have seen this when we have looked on the commutativity of these quantifiers. So therefore, you have to distinguish whether they are left or right of the existential quantifier. Let's look at an example how this works. So we have here already our penguin example in the Prenex normal form, and now we look at the quantifiers and we see here, the very first existential quantification, it's on number 1, which means there is no universal quantification left of it. So this is pretty simple. So therefore, we substitute this existential quantification simply by a new variable and by a new constant. So x here is substituted by a new constant a, and we are talking about penguin a and black and white a. So let's look further. We have still another existential quantifier that we have to treat somehow. And the other one, we see that there is one universal quantification left of it. So what we have to do here is simply, okay, therefore a new function is introduced for this variable set, and this function is dependent on the variable of the universal quantifications that are left of it, and this is only y. So therefore, for the last line, for the variable set, we introduce a function, new function, over the variable y of the universal quantifier. And you see the entire Skolem normal form is ready. We only have one universal quantification over a variable y. So only the variables which are universally quantified are still in the expression. Everything else is either a constant or a function over the variables that we have to consider. So this then is the Skolem normal form. Yeah, you see we are getting closer. Now we have to remove the existential quantification, and therefore there are only universal quantifiers, which means this should hold for all variables. Therefore we also can remove that quantifier and stay with the variable expression that we have here. So this is pretty easy. So we simply get rid of all the universal quantifiers. The variables we have are still there. And what we have to do now is simply we have to transform with the help of logical equivalences the formulas to a conjunction of disjunctions. And for that, you can make use, for example, of the distributive law. So let's have a look how that looks. So again, we transform the Skolem normal form to a conjunctive normal form by first getting rid of all the universal quantifiers. We don't need them anymore. And then via several steps, I have not included every single step that we need to translate it, we will get finally, as you see here, to a conjunction of disjunctions. So the disjunction symbol is here in red and the conjunction symbol in blue. And you see here, it's a four-line expression. It's a little bit bigger than the original one. But this, of course, occurs when you apply the distributive law. You will get more terms in the end. And sometimes for better readability also, you translate this, of course, then into clausal form for further work. So this now means you substitute simply the clauses, which are the disjunctions, into curly braces, and of course then make again curly braces over all the clauses, and you will end in a clausal form that you see here. So this then is the clausal form, and this is the end what we want to achieve. This is the canonical form of exactly our original penguin expression. One remark on the side, so these normal forms of course have several properties, and as you have seen, we have, due to logical equivalences, of course the logical equivalence transformation, this means the formula still stays the same, but we also have this a little bit strange Skolem normal form, and this exactly is the one who makes some problems. So if you look at that, and if f is in formula, and let's say the first transformation into Prenex form, normal form is g, the next transformation in Skolem normal form is h, and k would be the clausal form, then it would hold that f, of course, is equivalent to g, because between the Prenex normal form and the original formula, there have only been logical equivalence transformations. Likewise, between the Skolem normal form and the Clausius normal form, they are also equivalent because only equivalence transformation took place. But the Prenex normal form and the Skolem normal form, they are not exactly equivalent expressions. You saw that simply we substituted an existential quantification by one of the variables. So this is not necessarily equivalent because there might exist more. So you might argue, okay, we have here a transformation which breaks somehow the equivalence. So therefore, why can I say that I really have then a canonical formula which I can use for further automatic processing and reasoning? So the point is, we don't show this here in the lecture, but you can look it up in the books, or you can see this or see the proof in another lecture about logics. Nevertheless, it holds that f is not satisfiable, so the original formula, it's a contradiction, exactly if also the Clausius form is a contradiction. And again, this will be the basis of one of our inference algorithms for first-order logic, which is called resolution. And you see again here the proof has again to turn around. You do a proof by refutation. So you simply show, or the algorithm again then will show that we will have a contradiction. And the basis of that is, of course, these properties of the normal forms, which stay consistent over contradiction. And this is a property that we require for that. So let's look at an example of the Skolemnization and why this is not an equivalence relation. So let's consider the following formula. It's pretty simple. We have here in tautology. So we say there exists an x for which holds p of x, or there not exists an x for which p of x holds. So this is a disjunction of a statement and its negation. So therefore, this is always a tautology. Let's transform it to a negation normal form. So it means in front of the second existential quantification, we simply try to put the negation inside the bounded variable, which changes the polarity of the quantifier. So we have for all x, it holds that not p of x. Then we can simply make the Prenex normal form. So we substitute the second variable via a new variable, which is a y, and then put all the quantifiers in front of the entire formula. And then we do the Skolemnization, so we only have to consider the existential quantifiers here. We only have one. We have no universal quantification left of it, so therefore we can simply substitute it via a new variable a. And then you will see the formula that we have here on the slide. So for all y, it holds that p of a or not p of y. So why is this not in tautology? For that, we simply have to find an assignment or interpretation for which this formula computes false. And we can do that. And you see this more simpler or more easier if we simply try to do another logical equivalency. So we apply a logical equivalency and transform this Skolem normal form to the following. We can get, of course, p of a out of the bounding or binding of the variable y, because p of a is not dependent on y, so we can put it outside the scope of this binding, and then we have p of a or, and then there would be for all y, it holds that not py, and of course it's logically equivalent if we then put the negation out of the binding, which would result into a negated existential quantification. So these two, the Skolem normal form and the fourth line, they are logically equivalent. So now I have to find an assignment. So it means a variable assignment which somehow produces something which is not in tautology. And this is pretty simple. So we can say, okay, first we define an interpretation for p of a, which should compute false. And then we substitute or we assume that there exists another assignment for p of b, which computes to true. So this would fulfill the existential quantification here. And then we negate it. And then we have false or not true, which means false or false, and this computes to false. So here we would have an interpretation which is wrong. And therefore, it's not a tautology. And we see exactly, this is one of the reasons, or here we have shown that the Skolem normal form is not an equivalence transformation. And therefore, yeah, we have to take care. But the point is, what I've shown you on the slide before, that for if f is a contradiction, then after the Skolemnization, the resulting form still is a contradiction. And we will use this for our proof algorithm that we will show in the next part or in the next extra part of the lecture, which is the so-called resolution algorithm.